In this lecture, we'll learn how Hubble's law tells us the age of the universe, how the expansion of the universe affects distance measurements, and why the observable universe has a horizon. We left off with Hubble measuring the distances to galaxies and the finding that the farther the galaxy, the faster its velocity away from us. We also learned that Hubble's law says the velocity of a galaxy is proportional to the Hubble constant times the distance to the galaxy. But what does all this mean for our universe? The fact that distant galaxies are moving away the fastest implies something fundamental. Our universe is expanding. When I was a young sprout and first learned about the expansion of the universe, I thought everything was expanding. Me, coffee cups, rulers, everything. But this isn't what's going on. It's the space between galaxies that is expanding, not the stuff inside the galaxies. Within galaxies and galaxy clusters, there is enough gravity to hold things together. We observe that galaxies across the universe are moving away from one another. This implies that galaxies must have been closer together in the past. Tracing this convergence back in time, we reason that all matter in the observable universe started very close together. The entire universe came into being at a single moment. But the universe isn't expanding into anything. There's the universe, and that's it. Worse yet for our brains to think about is that the universe doesn't appear to have a center or an edge. The distribution of galaxies appears to be relatively smooth, meaning that no matter where you look or where you live in the universe, the overall appearance of the universe is the same. The idea that matter in the universe is evenly distributed without a center or an edge is often called the cosmological principle. The cosmological principle has not been proven beyond a doubt, but it is consistent with all observations to date. We can use Hubble's constant to determine how long the universe has been expanding, which is essentially the age of the universe. The velocity of anything is the distance it travels over the time it takes to travel that distance. To see how long it takes to get anywhere, you divide the distance you traveled by your velocity. For example, if you drive for 100 miles at 50 miles per hour, it takes you 2 hours. We can calculate how long galaxies have been speeding through the universe in the same way. We know their velocities from observing the Doppler redshift, the distance we can obtain via Hubble's law. The time since that the universe has been expanding is equal to 1 over the Hubble constant. The age of the universe is, then, the inverse of the Hubble constant. A larger Hubble constant will give us a younger universe, and a smaller Hubble constant will give us an older universe. For a Hubble constant of 22 kilometers per second per million light years, we calculate the age of the universe to be about 13.6 billion years. We've been assuming a constant rate of expansion, but what if the universe was expanding more quickly in the past? If that were the case, then the universe would have reached its current size faster than we think. The universe would actually be younger. If the expansion rate of the universe is increasing, and we think it is, more on that later, then the age of the universe would be greater. You may have been wondering, if the universe is expanding and galaxies are flying away from us, then how do we ever really know how far away something is? Well, we can't. For stuff that's nearby, universal expansion isn't a problem. But for way distant galaxies, distances can get confusing. We therefore define a look-back time. This is the time it takes the light from a distant object to reach us. Look-back time is unambiguous. If the look-back time is 600 million years, the light really traveled through space for a period of 600 million years to reach us. To get an idea of how this works, imagine our Milky Way and a distant galaxy 400 million years ago. A supernova explosion occurs in the distant galaxy. Photons of light travel in all directions away from the supernova. Because space is expanding, the distance between the Milky Way and the galaxy gets larger. The photons of light that reach us from the supernova took 400 million years. Therefore, we say the galaxy has a look-back time of 400 million years. An object's look-back time is directly related to its redshift. The expansion of the universe stretches out all the photons within it, shifting them to longer, redder wavelengths. We call this effect a cosmological redshift. We can think of the redshift as being caused by either the Doppler effect as the galaxy moves away from us, or from the expansion of space, stretching the photons out. For very distant galaxies, it's preferable to interpret the redshift as coming from the expansion of space, because as space expands, galaxies are being carried along with it rather than flying through it. I mentioned earlier that the universe doesn't appear to have an edge, but the universe does have a horizon beyond which we cannot see. The cosmological horizon marks the limit of the observable universe. It's a boundary in time, not space. It exists because we cannot see back to a time before the universe began. The universe is about 14 billion years old, so therefore the look-back time of the cosmological horizon is about 14 billion years. The distance to this horizon is in fact much greater because of the expansion of space. It's actually around 47 billion light years. I'll leave you here to ponder the enormity of our universe. Take care, and I'll talk to you soon.